So we're starting here. When a weak acid and a strong base are mixed, if the weak acid is in excess, right? If the weak acid is in excess, that means it's going to eat up all of the base. It's going to eat up all of the base. So I said all the base is used up, leaving only a weak acid and the conjugate base left. And we know a weak acid and a conjugate base is a what? A buffer. And a buffer can neutralize acid or base. A buffer can neutralize an acid or a base. So that is where we are starting off today. Next one says, for titrations of weak acids and bases, it's useful to consider the point halfway to the equivalence point when there are equal concentrations of each species. Equal concentrations. pH equals pKa when the conjugate base have equal concentrations. Using Henderson-Hasselbalch to prove pH equals pKa, it says use it to prove it. Okay, well this is easy to prove because we know that pH equals pKa plus log of A minus, concentration of A minus, over the concentration of HA. And I know that the log, so if I rewrite this, pH equals pKa plus log of, if those are the same, it's going to be log of 1. What is the log of 1? 0. That turns into 0. So this is canceled out. Therefore, pH equals pKa. Answer the following questions about the solution of nitrous acid and sodium nitrite. The Ka of HNO2, oh crap, I need a calculator. The Ka for HNO2 is 7.2 times 10 to the negative fourth. So the pKa, negative log of 7.2, second E, negative 4. pKa I got is 3.14. Can anybody confirm that for me? That's what you got? Okay. Next one. Mix 1 milliliter with 0.250 molar HNO2. What should I do with these first two things? Turn it into moles, right? So 0.001 times 0.250. This gives me 2.5 times 10 to the negative fourth moles. And then what's 10 divided by 1,000? So 0.01 times 0.250. This gives me 2.5 times 10 to the negative second moles. Then I have to divide both of these by what?
2.5.
You're right. I promise you, I just can't count. 1, 2, 3. Thank you. I'm going to divide those both by what? 0.011. Because I have to add those two volumes together. Yes? What's up, Mr. Worth?
Are you going into Chem Lab history?
Tomorrow.
Okay. So I can set up there.
Yep. 0.011 liters. So I'm going to divide those. So I have 2.5 second E, negative 4, divided by 0.011. This gives me 0.02, I guess I do 2 to the decimal, 3 molar. And then 0.0025 divided by 0.011. This gives me 0.02, oh geez. Wait, how did I get the same thing there?
-4 and -3.
Is one of these wrong?
Yeah, maybe it should just be 0.24.
Oh yeah, I was going to say, those should not be the same. 0.23 molar. That looks better. Thank you. So, what is my pH? So what am I going to do with these two numbers? I have the pKa, right? I'm going to Henderson-Hasselbalch the heck out of this thing, right? So pH equals 3.14 plus log of, which number is going to go on the top?
No, it's
The 0.23 is going to go on the top, right? 0.23 over the 0.023. So this is log of what? 10. Log of 10 is 1. 3.14 plus 1 is 4.14. So my pH equals 4.14. So that's how I would do a question like that. Flip it, and there's going to be a big old blank. Hey, what's up?
Are the black lights where they should be, or should they be all in like one spot?
They need to be spread out to cover the whole lab. So we kind of have them spread as a rough estimate.
Okay. I'm not gonna do this one. I thought they needed to be together.
You'll know by turning off all the lights and making sure you can see the stuff on all the walls.
Oh, that's fine.
That's your test. Okay. Did I hit record? I did. How'd you know? Thank you for believing in me. That means a lot. Okay. A mixture of HNO2 and NaNO2 has a pH of 2.5. What is the concentration of A minus over HA? So, this is easy, because we know that pH equals pKa plus log of what? Concentration of A minus over the concentration of HA. What are they asking me to solve for? For this, right? I know the pH, agreed?
Yeah.
Okay, what was my pH?
No, it's 2.15.
This time it's 2.15. So 2.15 equals, we are still going to use our original pKa because they haven't told me anything different, which was what? 3.14 plus log of, can I just say x? Plus log of x. So we need to solve for x. So solve for x, tell me what you get. What'd you guys get? You gotta unlog it. That's not what I had. I had 0.102. So I think you're off by a log somehow if you had 10. 0.102. So 0.102 equals my concentration of A minus over my concentration of HA, which would mean how much of this has dissociated? 10%, right? Yes? So that's what we're saying here. 10% is dissociated. Okay. How many milliliters of 2.75 molar NaOH must be added to 0.150 molar acetic acid to make 125 milliliters of a buffer solution with a pH of 4? The Ka is 1.8 times 10 to the negative fifth. So what are we going to do on this? I'm going to do Henderson-Hasselbalch again. So I'm going to say pH equals pKa plus log of A minus over concentration of HA. Did they give me a pH? They did. So the pH is 4 equals, what is the negative log of this? 4.74 plus, do I have any of the other things? I don't really have the other things. But I can solve for the 0.182 plus log of x. So when you do that, x equals 0.182. So 0.182 equals this term, right? So 0.182 equals my let's see, 2.75, I solve for x. I solve for x. 0.275 times x. X is what I'm solving for because I want to know the milliliters of sodium hydroxide divided by 0.150 times 125. These numbers? 2.75 molar. I'm trying to figure out how many milliliters. This equation? This is just, I solved for, x was A minus over HA. So I'm saying 0.182 is A minus, which would be the concentration of 2.75 times milliliters over 0.150 times milliliters. You can convert it to liters, it's going to be the same thing, same ratio. So now I'm going to solve for x here. So I just set this 0.182 equal to A minus over HA. Are you okay with that, Emily?
Yeah, I don't know where the 4.74 came from.
4.74, the negative log of this.
Okay.
Just took the negative log of that. What'd you guys get for x? Anybody? That's what I got. I had 1.24 milliliters. 1.22 would be fine. 1.24 milliliters. Now, let's see if that makes sense. My pH was 4, which means that this is acidic or basic? Acidic. And I had 125 milliliters, or let's see, 125 milliliters of the solution. Yeah, so I would say that makes sense. Because this 1.24 milliliters was of the strong base. So I think realistically, just conceptually thinking about it, that makes sense. It wouldn't take much. Normal blood pH is 7.4. If your blood pH is less than 6.8, if your blood pH becomes less than 6.8 or more than 7.8, death, wow, that escalated quickly, can occur. When you exercise, glucose is broken down in your cells. So good for you. Producing CO2 and H+, which go into blood to be eliminated from your body. This causes your blood pH to do what? Drop. Why?
H plus down.
There you go. Your blood H plus makes down. Yes. Did you guys read through the write this, not that? It's super good. I would highly recommend reading through that sometime in the next 6 days. Because it'll say like what you could write. Like an example would be, don't write like dissolves like. And it'll say, do write solutions with similar intermolecular forces will dissolve in each other. Something like that. It's really good. That's really good. It'd be worth a read if you get the time between now and Monday. Probably 10-minute read. Also, Ed Puzzles due Friday. Also, Thou Shalt Not Forget. Make sure you've uploaded your best score. Still time. Still time. Okay. Correct. Yes. Friday. Your blood contains buffers that help prevent changes in pH, which is good, because this is not a large range, all right, to die. I've only had one near-death experience this year. That's not bad. I don't know if it was near-death. My wife thought I was dying. I don't know. She thought I was stroking out, so it's true. That's what she thought. She thought I was stroking out and dying. She does. She gave me chest compressions, okay?
I think that's near death.
I would say that's fairly near death. I don't know.
Yeah, chest compressions, that's near death.
Anyway. Well, she wasn't sure if I was breathing because she had just learned about, there's some special type of breathing you're supposed to do it for if you're not, if they're like breathing really light. She thought that's what I was. But either way, she kept my blood flowing. So, and then I started doing this during my seizure, I guess. So then she knew
Women.
that, no, I was pushing her away.
Oh.
So, anyways, traumatizing for her. I feel so bad for her. I've apologized many times for having a seizure. I mean, obviously it's not my fault. Well, I don't know. I had a lot of salt that night. I don't know. That's the only thing that I can think that's said about. I also had not had Mountain Dew in 26 days. It was day 26. Was it day 23 or day 26?
I thought it was 24.
Somewhere in there.
It was day 24.
It was in the third week. All right.
I mean, now you know the limit.
Yeah, but then I went another like 40 days after that. I don't know.
Just building up your tolerance to it.
Yeah.
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 I have to go 50 with that.
So thanks to that,
When you're reminded.
but you know what? As of tomorrow, I can rock climb. So, yep. Rock climbing privileges are back. Still can't swim by myself, but I can rock climb.
Mr. Heller, I think when the seniors leave, you take Reese and I rock. To celebrate.
So when I go swimming this summer, Aiden has a really important job because I may have a seizure and die. So, just saying. Let's finish this. We talked about steak second period, so get ready for that. One buffer is carbonic acid and its conjugate base, the bicarbonate ion. The normal ratio is 10.5. An individual with diabetic acidosis. I have had a lot of I'm like kind of hyped right now.
He hates biology. So.
I do. My brain just shuts down. An individual with diabetic acidosis, sounds like bad breath, has pH, it does, doesn't it?
Not what it is.
I know, of 7.32. What is the ratio of this patient? What is the ratio of this patient? Once again, Henderson-Hasselbalch. So, pH equals pKa plus log concentration of A minus over concentration of HA. So first thing I need to do is I need to get my pKa. So the negative log of 4.2 times 10 to the negative 7th is what? Someone do that quick. 6.38. Are you good with that? Okay. So the pH, they gave me a 7.32. So 7.32 equals 6.38 plus log of your A minus, which is going to be I'm just going to write it out. HCO3 minus over H2CO3. So once again, we are solving for X. We're solving for X. What do you get when you solve for X? So what does this term equal? Do we agree with that? 10 to the negative, right?
That's what I did, and it's not right.
What'd you get?
Yeah, not negative.
Oh, just 10 to the...
This is subtracted
So what did you guys get?
to 8.7.
Do I have another person to confirm that?
Yeah.
8.7. Based on the answer above, which species of the buffer is being depleted? Well, this is a number greater than 1. Agreed? So therefore, what is getting depleted? The numerator, right? So that means that HCO3 minus is the one being depleted because this number is greater than 1. Yes? Cool with that? Flip it. Consider the buffer depicted to the right. Picture. The pKa is 7.4. Is the pH of the buffer greater than, equal to, or less than 7.4? Use the Henderson-Hasselbalch to explain how you know. So the pKa is 7.4. What about the pH? So looking at the picture, here's what I would do. I would say that HA is my big dot, little dot, right? And I would say that A minus is just big dot. Yes? So count. 1, 2, 3, 4, 5, 6, 7. I have 7 of those. And I have 1, 2, 3, 4. I have 4 of those. So this means that my log term is going to be 4 over 7. Right? My log term is going to be 4 over 7. So that's less than 1. So what is log of 4 over 7? Is it positive or negative? It's negative. Therefore, my pH is going to go down. You got it. This is a negative number, so pH goes down. This is a really good question. I could see something like this being on the AP test as a multiple choice or as a short FRQ. As a short FRQ. That'd be a great FRQ. Buffering capacity is defined by the quantity of strong acid or strong base must be added to 1 liter of a solution by changing it by what? Blank pH unit. What would you say? Yeah, 1. By 1 pH unit. He shoots his scores. You have 1 liter of buffer A containing 0.5 molar HNO2 and 0.5 molar NO2 minus with a pH of 3.25. What is the pH after adding 0.035 mole HCl? Assume that the volume of HCl is negligible. So, what ion am I adding to this buffer? H plus. Which one of these things can accept H plus?
NO2 minus.
Yes. So I'm going to write NO2 minus plus H plus is going to give me HNO2, which I'm going to, HNO2 plus water. Plus water. How much NO2 minus am I starting out with?
0.5 molar.
0.5 molar. How much H plus am I starting out with?
0.035.
0.035.
Molar though, that's just moles.
Oh.
But it says assume the volume is negligible.
Is this 1 liter?
What?
Where? Oh, 1
Oh,
liter.
in the beginning.
You have 1 liter, yeah. So it is molar. So it is molar. It also says the volume is negligible, so we'll just say it's molar. How much HNO2 am I starting out with? 0.5 molar. Water's not part of this because it's liquid, right? What's my change?
Adding HNO2.
Nope.
0.035.
What?
You got 0.035.
I'm going to subtract. You got it. Subtract the 0.035 because I'm going to use it all up. Minus 0.035 minus 0.035 plus 0.035. I know. So this gives me 0.465, 0, and 0.535. Do I have HA and A minus? Guess what I'm going to do? Henderson-Hasselbalch.
Yippee!
pH equals pKa plus log of, it's going to be 0.535, no, 0.465, right? 0.465 divided by 0.535. My pH is what I'm solving for. No, they gave me pH. 3 point. What's it asking for?
pH change.
Oh, what's it after? Do they give me a pKa?
No, they give you the pH of the original well.
Let me picture the original.
So yeah, we can find.
Oh, the original PKA is just 3.25.
Do they give me an original pKa? No, that's the pH.
But
The pH.
the concentration at that pH is just one, it's a singularity.
You're right. So the pKa, the pH would be 3.25. We'd have to assume it's equal.
Yeah, we have to assume it's equal.
Yes. So it's going to be 3.25 plus that log term.
How do you do that? It doesn't give us the volume, so we have to just assume.
It's a buffer solution, right?
Oh yeah, that's it.
0.5 moles, 0.5 moles. If they're half and half, this must be at the halfway point, right? They're equal. So, is that a Klondike? How dare you? I bought all those popsicles.
It was the only one that was in the freezer,
Where was it?
our freezer.
Oh, where did it come from?
Mrs. Joyce.
Oh, fine. I'll let it pass. I'll let it slide. It's
Brought
fine.
me a dessert.
She's a keeper.
I know. Especially after 35 years.
Yeah,
37 next year.
definite keeper. I've only been married to my wife a third of that time.
And she's
Wow.
never brought you a Klondike bar.
True. She's got time though. What'd you get? 3.19. 3.19. Now, this second part is asking you to do it again.
Why?
I'm not going to do it all again. So you do it again. All right? You do it again. I'm going to throw this up here. And you get 2.5. So after you do it again, you get 2.5. I'm throwing this up there so it's recorded. So you do that whole thing again, and you get 2.5. So, what's that?
What did they change?
They just changed your. Let's see. What did they change? 0.035, 0.05. Oh, it's 0.05 and 0.05. So that makes sense because here's what they want you to answer. Consider your results from the previous two questions. Buffer solution A has a what? Higher buffer capacity, right? Why? Greater buffer A had a 0.5 molar and a 0.5 molar, right? Buffer B had 0.05 and 0.05. Had 0.05 and 0.5. Had less. Less molarity. You now experiment by adding 0.035 KOH to the buffer A. Which buffer will have least change in pH? Without doing math, how do you know? So I add KOH to this, which is going to have the least change. Yeah, buffer A. Why? Higher capacity. Yeah, buffer A, higher molarity, higher capacity. It can eat. Buffer A wants to eat more. Let it eat. Here we go. Down here, buffer 1, buffer 2. Between buffer 1 and buffer 2, which has the highest capacity for absorbing 0.2 moles of 0.03? Don't overthink this. Buffer 1, buffer 2, which one? Why?
Because it has more moles.
Yeah. Do you have a second one on your page or not?
What? Yeah, there's this one.
Let's go flip it. What about 0.03 moles of NaOH? Buffer 1 or buffer 2?
Two.
Buffer 2. Why?
More moles.
Higher molarity. Now look over here. Between 3 and 4, which has the highest capacity for absorbing 0.2 milliliters of HNO3?
3.
Why?
Because there's more moles of the one without.
Yes. You got it. So these moles are not equal. These molarities are not equal. So buffer 3 has more moles of the base. So 0.03 moles of NaOH, which one is that going to be? Buffer 4. So out of these three buffers, which one has the highest pH? Which ones can you immediately get rid of? 1 and 2. What is their pH? 7, right? Those are neutralized.
Why would it be 4 on this last one?
Well, I haven't answered this yet. First, which has the highest pH? 4?
Yeah, that.
Because buffer 4 has the most protonated. It's going to rip that H off.
My bad. I thought that was an acid.
The NaOH wants to rip that H off and turn it into water. So which has the highest pH? Buffer number 3. Which has the lowest pH? 4. 3 is going to be above 7. 4 is going to be below 7.